Right now, as you watch this video, your brain is performing an impossible task. It's trying to imagine something that may not exist, the moment before time began. Every neuron firing in your head, every thought forming in your consciousness operates within time. Past flows into present, present into future. But what happens when you try to think about a moment before moments existed? What happens when you ask, what came before the Big Bang? This isn't just a philosophical puzzle. This is the question that has fractured physics into competing camps, driven brilliant minds to the edge of comprehension, and forced us to confront a terrifying possibility: that the universe might be fundamentally stranger than our brains are capable of understanding. In 1927, a Belgian priest named Georges Lemaitre stood before the scientific establishment with an idea so radical it was initially dismissed as religious fantasy. He proposed that the entire universe emerged from what he called a primeval atom, a single point of infinite density that exploded outward in a cosmic fireball. Albert Einstein himself told Lemaitre his physics was abominable. But within decades, evidence mounted. The universe was expanding. Galaxies were racing away from each other, and if you ran the cosmic film backward, everything collapsed into a single point: the Big Bang. But here's where the comfortable story ends and the nightmare begins. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Time and space emerged together, woven into a single fabric that physicists call space-time. Before the Big Bang, there was no before. There was no stage on which events could unfold, no clock ticking in the void. Asking what came before the Big Bang is like asking what's north of the North Pole. The question itself might be meaningless, yet we can't stop asking, because 13.8 billion years ago, something happened. The universe began. And every instinct we have, every pattern our brains have evolved to recognize, screams that effects must have causes. Beginnings must have befores. The universe can't simply start without something starting it. This is the paradox that haunts modern physics, and the solutions physicists have proposed are more unsettling than the problem itself. Let me take you to Princeton University in 1982. A young physicist named Paul Steinhardt was working on a problem that seemed unrelated to cosmic origins. He was studying the mathematics of phase transitions, the way water transforms into ice, the way magnetic fields suddenly organize themselves. But as he worked through the equations, he noticed something extraordinary. The mathematics describing these transitions looked eerily similar to the mathematics describing the early universe. What if, Steinhardt wondered, the Big Bang wasn't the beginning at all? What if it was just a phase transition, like water freezing into ice? What if our universe was part of an eternal cycle, expanding and contracting, dying and being reborn, over and over again, forever? This is the cyclic universe model, and it offers a seductive answer to our question. There was no before the Big Bang, because the Big Bang was just one beat in an infinite cosmic rhythm. Before our universe, there was another universe. Before that, another. An endless chain of cosmic deaths and rebirths stretching backward through eternity. Imagine compressing all of cosmic history into a single day. The Big Bang happens at midnight. Stars form by morning. Galaxies cluster by afternoon. Life emerges on Earth in the final seconds before midnight. And then, as the clock strikes 12 again, everything collapses. The universe contracts. Matter and energy compress back into a single point. And then, in a new cosmic dawn, another Big Bang erupts. Another universe begins its 24-hour cycle. In this model, time has no beginning. The universe has always existed, cycling through infinite iterations. Each cycle might last trillions of years. The laws of physics might be slightly different in each iteration. Perhaps in the previous universe, stars burned blue instead of yellow. Perhaps gravity was stronger or weaker. Perhaps life never emerged at all. But here's the problem that keeps physicists awake at night: entropy. The second law of thermodynamics states that disorder always increases. Coffee cools down, never heats up. Broken eggs don't spontaneously reassemble. The universe is running down, dissipating energy, sliding toward a state of maximum disorder called heat death. And if the universe cycles eternally, each cycle should be more disordered than the last. Eventually, after enough cycles, the universe should be a uniform, lifeless soup of particles at the same temperature, incapable of forming stars or galaxies or anything interesting at all. Yet here we are, in a universe full of structure and complexity. Which means either the cyclic universe model is wrong, or something is resetting entropy with each cycle. Something is winding the cosmic clock back up. But what? And how? This is where the second theory emerges, and it's even more disturbing. In 1973, a physicist named Edward Tryon was sitting in a seminar at Columbia University, half listening to a lecture about cosmic origins. Suddenly, he blurted out an idea so strange that the room fell silent. Quote 4, he said. Quote 5. The other physicists laughed. They thought he was joking. He wasn't. Quantum mechanics, the physics of the very small, reveals that empty space isn't actually empty. The vacuum seethes with activity. Particles pop into existence from nothing, exist for a fraction of a second, then vanish back into the void. These are called virtual particles, and they're not theoretical abstractions. We've measured them. We've detected their effects in laboratories around the world. Now imagine this. What if the entire universe is just a particularly large quantum fluctuation? What if 13.8 billion years ago, the laws of quantum mechanics allowed a tiny bubble of spacetime to spontaneously appear from nothing, and that bubble inflated into everything we see today? This is the quantum fluctuation theory, and it suggests something profoundly unsettling. The universe came from nothing. Not from a previous universe, not from a divine creator, from nothing. Absolute, total, complete nothing. But here's where language starts to fail us, because quote 6 in quantum mechanics isn't the same as nothing in everyday speech. The quantum vacuum isn't empty space. It's a roiling sea of potential, governed by laws, filled with fields and forces. It's something, not nothing. So the question just shifts. Where did the quantum vacuum come from? Where did the laws of quantum mechanics come from? Some physicists argue we're asking the wrong question. Perhaps the laws of physics don't come from anywhere. Perhaps they simply are, eternal and unchanging, the bedrock of reality itself. But this feels like giving up, like declaring that at some point, explanation must end, and we must simply accept the universe as a brute fact. Others propose something even stranger. In 1981, a physicist named Alan Guth was working on a problem in particle physics when he stumbled onto an idea that would revolutionize cosmology. He called it inflation. The theory proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size every tiny fraction of a second, inflating from smaller than an atom to larger than a galaxy in less time than it takes light to cross a proton. Inflation solved several problems in cosmology. It explained why the universe looks the same in all directions. It explained why space is flat rather than curved. But it also led to a bizarre implication, developed by physicists like Andrei Linde and Alexander Vilenkin. If inflation happened once, it's probably still happening. Somewhere. Imagine the universe as an infinite ocean. Our Big Bang was a bubble forming in that ocean. But the ocean itself is eternal, and bubbles are constantly forming, each one inflating into its own universe with its own laws of physics, its own constants, its own history. Some bubbles produce universes where stars can form. Others produce universes that collapse immediately. Others produce universes so strange we can't even imagine them. This is eternal inflation, and it suggests that our universe isn't the universe. It's one bubble in an infinite foam of universes, each one emerging from the eternal inflating background, each one with its own Big Bang, its own beginning. But the background itself, the inflating ocean, has no beginning. It's eternal. So what came before our Big Bang? Another region of the eternal inflating multiverse. And before that, more inflation. And before that, inflation all the way down, forever. But this theory has a problem too. If inflation is eternal into the future, is it also eternal into the past? In 2003, physicists Arvind Borde, Alan Guth, and Alexander Vilenkin published a theorem that shook the foundations of eternal inflation. They proved mathematically that any universe undergoing eternal inflation must have had a beginning. You can't have inflation forever into the past. At some point, there must be a boundary, a moment before which inflation wasn't happening. Which brings us back to the original question. What came before? And this is where physics reaches its breaking point. In 1983, two physicists named James Hartle and Stephen Hawking proposed an idea so radical it still divides the scientific community. They suggested that asking what came before the Big Bang is like asking what's north of the North Pole. Not because we don't know the answer, but because the question itself is based on a misunderstanding of reality. Time, they argued, didn't always exist in the form we experience it. Near the Big Bang, as you approach the moment of cosmic origin, time becomes something else. It becomes space-like. The distinction between past and future blurs. The universe doesn't have a beginning in time because time itself emerges gradually from a state where it doesn't exist. Imagine walking north on Earth. As you approach the North Pole, the concept of underscore, quote underscore, 8 underscore becomes increasingly meaningless. At the pole itself, every direction is south. There is no north of the North Pole, not because something is blocking you, but because the geometry of the Earth makes the question meaningless. Similarly, Hartle and Hawking proposed, as you trace the universe backward toward the Big Bang, time gradually transforms into space. The universe doesn't have a beginning in time because time itself fades away. The universe is finite in the past, but boundless. It has no edge, no boundary, no moment of creation. This is called the no-boundary proposal, and it's one of the most beautiful and disturbing ideas in modern physics. Beautiful because it resolves the paradox. There's no before the Big Bang because before requires time, and time didn't exist. The universe is self-contained, requiring no external cause, no creator, no prime mover. Disturbing because it violates every intuition we have about causality and existence. It suggests that the universe simply is, without explanation, without reason, without purpose. It emerged from a state where time didn't exist, not because something caused it to emerge, but because the mathematics of quantum gravity allowed it to emerge. But here's the deepest problem. We don't know if the no-boundary proposal is correct. We don't even know if it's testable. Because to test it, we would need a complete theory of quantum gravity, a theory that unifies quantum mechanics and general relativity. And we don't have that theory yet. String theory offers one possibility. Loop quantum gravity offers another. Each approach suggests different answers to the question of cosmic origins. Some versions of string theory support eternal inflation. Others support cyclic universes. Some suggest the universe emerged from a collision of higher dimensional membranes called branes. Others suggest reality is fundamentally timeless, and the flow of time we experience is an illusion emerging from quantum entanglement. We don't know which, if any, of these theories is correct. And that's what makes this question so terrifying for physicists. Because we've reached the edge of what our current theories can explain. We've built telescopes that can see nearly to the moment of the Big Bang itself. We've detected the cosmic microwave background, the afterglow of creation, mapped across the entire sky. We've measured the universe's expansion rate, its age, its composition. We've confirmed that the Big Bang happened. But we can't see before it. We can't probe the moment of origin itself. Our equations break down. Our telescopes go dark. We're left with mathematics and speculation, with theories that may be untestable, with questions that may be unanswerable. Some physicists find this liberating. It means there's still mystery in the universe, still frontiers to explore, still questions that will occupy human minds for centuries to come. Others find it frustrating. We've come so far, understood so much, mapped the universe from the smallest quarks to the largest galaxy clusters. And yet, the most fundamental question of all, the question of why there is something rather than nothing, remains beyond our grasp. But perhaps the most unsettling possibility is this: maybe the question has no answer. Not because we're not smart enough to find it, but because reality itself doesn't provide one. Maybe the universe exists for no reason. Maybe it emerged from nothing, or from eternal inflation, or from a quantum fluctuation, not because something caused it to exist, but simply because the laws of physics allowed it to exist. And in an infinite multiverse, or an eternal timeline, everything that can happen does happen. This is the abyss that opens up when you push physics to its limits. Not just ignorance, but the possibility of fundamental meaninglessness. The possibility that the universe is a brute fact, requiring no explanation, admitting no deeper understanding. And yet, we keep searching, because that's what humans do. We ask questions, we build theories, we test them against reality. We refine our understanding, inch by inch, generation by generation. We've gone from thinking the Earth was the center of the universe to understanding we're on a small planet orbiting an ordinary star in an ordinary galaxy in an observable universe containing 2 trillion galaxies. We've gone from thinking time was absolute to understanding it's relative, woven together with space into a dynamic fabric that bends and warps. We've gone from thinking the universe was eternal and unchanging to understanding it had a beginning and is still evolving. Each answer raises new questions. Each solution reveals deeper mysteries. Let me show you exactly how strange these theories become when you examine them closely. Take the cyclic universe model. When Paul Steinhardt and Neil Turok refined this theory in the early 2000s, they weren't just proposing that universes repeat. They were describing a mechanism so precise, so mathematically elegant, that it seemed almost too beautiful to be wrong. They called it the ekpyrotic universe, from the ancient Greek word for conflagration. Picture 2 three-dimensional membranes floating in a higher dimensional space we cannot see or touch. These branes are like sheets of reality, each one containing an entire universe. For trillions of years, they drift through the higher dimension, slowly approaching each other. As they draw closer, the gravitational attraction between them intensifies, and then they collide. The collision releases enormous energy. Space itself ripples with the impact. Matter and radiation flood into both branes. From the perspective of observers within either brane, this collision looks exactly like a Big Bang. Time begins. Space expands. Particles form. Stars ignite. Galaxies cluster. Life emerges. But here's the crucial detail. The collision isn't the beginning. It's just an event in an eternal cycle. After the collision, the branes bounce apart. They drift through the higher dimension for another trillion years. Then they collide again. Another Big Bang. Another universe. Another cycle. In this model, what existed before our Big Bang? Another universe, living out its final trillion years before colliding with our brane. And before that, another cycle. And before that, cycles stretching backward through eternity, each one lasting perhaps a trillion years, each one producing a universe that lives and dies and is reborn. The mathematics works. The theory makes predictions. It explains why the universe is so flat, why the cosmic microwave background has the temperature fluctuations we observe, why space appears to be expanding at an accelerating rate. Every test we've performed so far is consistent with the ekpyrotic model. But there's a problem that gnaws at the foundations of this elegant theory. Entropy still increases. With each cycle, disorder accumulates. The branes should become more chaotic, less organized, less capable of producing structured universes. After enough cycles, the collisions should produce nothing but a uniform soup of particles, incapable of forming stars or galaxies or anything interesting. Yet here we are, in a universe full of structure, in what appears to be a relatively young cycle. Steinhardt and Turok proposed a solution. They suggested that during the long periods between collisions, when the branes are drifting apart, the universe undergoes a kind of cosmic cleansing. The expansion dilutes the entropy, spreading it so thin that each new collision starts with a nearly clean slate. The universe resets itself, not perfectly, but enough to allow structure to form again. But this solution raises new questions. How many cycles have there been? If the universe is truly eternal into the past, there should have been infinite cycles. And if there have been infinite cycles, even a tiny accumulation of entropy with each cycle should have produced infinite disorder by now. Unless the reset mechanism is perfect. Unless something is actively removing entropy from the system. And that something would require energy. It would require a mechanism. It would require, in essence, a cosmic engine running forever, powered by nothing, violating the very laws of thermodynamics it's trying to circumvent. This is the paradox that haunts every cyclic model. Eternity is a long time. Infinite cycles is a lot of cycles. And our universe shows no signs of being infinitely old or infinitely disordered. So let's turn to the alternative. Let's examine what it really means for the universe to emerge from nothing. When Edward Tryon proposed that the universe is a quantum fluctuation, he was building on one of the strangest discoveries in 20th century physics. In 1948, a Dutch physicist named Hendrik Casimir predicted that if you place two metal plates very close together in a vacuum, they should attract each other. Not because of gravity or electromagnetism, but because of the quantum vacuum itself. The space between the plates contains fewer virtual particles than the space outside the plates. This creates a pressure difference. The vacuum pushes the plates together. In 1997, physicist Steve Lamoureux measured this effect with exquisite precision. The Casimir force is real. The quantum vacuum has measurable physical consequences. This means the vacuum isn't nothing. It's a seething ocean of quantum activity where particles and antiparticles constantly pop into existence, exist for a fraction of a second, then annihilate back into the void. These virtual particles aren't just mathematical abstractions. They affect the energy levels of atoms. They contribute to the mass of particles. They shape the structure of reality itself. Now scale this up. Way up. In quantum mechanics, there's a fundamental uncertainty principle. You cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you measure one, the less precisely you can know the other. This isn't a limitation of our measuring instruments. It's a fundamental feature of reality itself. But the uncertainty principle doesn't just apply to position and momentum. It also applies to energy and time. For very short periods of time, the universe can violate energy conservation. A particle can borrow energy from the vacuum, exist briefly, then pay the energy back before the universe notices the debt. The shorter the time period, the larger the energy violation that's allowed. Now imagine the ultimate quantum fluctuation. A fluctuation so brief, so violent, that it borrows enough energy to create an entire universe. For a fraction of a second so small it makes a nanosecond look like an eternity, the quantum vacuum fluctuates. A tiny bubble of space-time appears, containing enormous energy. And then, instead of collapsing back into the void, the bubble inflates. This is where inflation enters the picture. The energy in the bubble drives exponential expansion. The bubble doubles in size, then doubles again, 60 times in the first fraction of a second. By the time inflation ends, the bubble has grown from smaller than a proton to larger than the observable universe. The borrowed energy converts into matter and radiation. The quantum debt is paid. And the universe continues expanding, cooling, evolving into everything we see today. In this model, what existed before the Big Bang? The quantum vacuum. A timeless, spaceless state of pure potential, governed by the laws of quantum mechanics, capable of spontaneously producing universes. But here's where the theory becomes deeply unsettling. If the quantum vacuum can produce one universe, it can produce infinite universes. Every possible quantum fluctuation that can happen does happen, somewhere, somewhen, in the eternal foam of the quantum vacuum. Most fluctuations are tiny, producing virtual particles that vanish immediately. But occasionally, very occasionally, a fluctuation is large enough to inflate into a universe. Our universe is one such fluctuation. But there are others. Infinite others. Each one emerging from the quantum vacuum, each one with its own Big Bang, its own laws of physics, its own history. Some of these universes last for trillions of years. Others collapse immediately. Some produce stars and galaxies and life. Others are sterile, lifeless, governed by laws that prevent complexity from forming. And here's the truly disturbing part. In this model, there's no reason our universe exists. No purpose, no design, no meaning. We're just a random quantum fluctuation that happened to inflate into a universe capable of supporting life. We're cosmically, fundamentally, irreducibly accidental. Some physicists find this idea liberating. It means the universe doesn't need a creator. It doesn't need a first cause. It can emerge spontaneously from the quantum vacuum, governed by laws that are themselves eternal and unchanging. Others find it deeply troubling, because it pushes the question back one level without really answering it. Where did the quantum vacuum come from? Where did the laws of quantum mechanics come from? Why do those laws allow universes to form rather than preventing them? Why is there a quantum vacuum rather than absolute nothingness? The physicist Lawrence Krauss wrote a book titled A Universe from Nothing, arguing that quantum mechanics explains how the universe can emerge from nothing. But philosopher David Albert pointed out a crucial flaw. The quantum vacuum isn't nothing. It's a complex, structured entity governed by laws. It's something, not nothing. So the question remains, where did that something come from? This is where physics reaches its conceptual limit. Because every explanation requires something to explain. Every cause requires a prior cause. Every law requires a framework in which that law operates. At some point, explanation must end. At some point, we must accept something as simply given, as the bedrock of reality that admits no deeper justification. But which bedrock? The quantum vacuum? The laws of physics? The mathematical structures that describe reality? Or something else entirely? Let's examine the third major theory, eternal inflation. Because this theory suggests something even stranger than cyclic universes or quantum fluctuations. It suggests that the Big Bang wasn't a unique event. It's happening constantly, everywhere, forever. When Alan Guth proposed inflation in 1981, he was trying to solve specific problems in cosmology. Why is the universe so uniform? Why is space so flat? Why don't we see magnetic monopoles, exotic particles that should have been produced in the early universe? Inflation answered all these questions. If the universe underwent a brief period of exponential expansion in its first fraction of a second, it would smooth out any initial irregularities, flatten space, and dilute exotic particles to undetectable levels. The theory was elegant, powerful, and made testable predictions. But André Linde realized something profound. If inflation happened once, it probably never stops. Here's why. Inflation is driven by a field called the inflaton field, which permeates all of space. When this field has high energy, space expands exponentially. When the field's energy drops, inflation ends, and the energy converts into matter and radiation. This is what happened in our universe. Inflation ended, the inflaton field decayed, and the Big Bang began. But quantum mechanics introduces uncertainty. The inflaton field doesn't decay uniformly everywhere. In some regions, it decays quickly. In other regions, it remains high. And in regions where it remains high, inflation continues. Now here's the key insight. Inflation expands space faster than the inflaton field can decay. Even though some regions stop inflating and become universes like ours, the regions that continue inflating grow faster. The total volume of inflating space increases exponentially, forever. Imagine a forest where trees occasionally stop growing and produce seeds. But the forest itself expands faster than trees can stop growing. The forest grows forever, constantly producing new seeds, each seed becoming a new tree, each tree eventually producing more seeds. The forest has no boundary, no edge, no end. It's eternal and infinite. This is eternal inflation. Our universe is one seed, one region where inflation ended and matter formed. But the forest continues growing. Other seeds are constantly forming, other universes constantly emerging, each one with its own Big Bang, its own physical constants, its own history. In this model, what existed before our Big Bang? The eternally inflating background. A region of space undergoing exponential expansion, governed by quantum fluctuations, constantly producing bubble universes like ours. And before that, more inflation. And before that, inflation stretching backward through time, possibly forever. But here's where the Borde-Guth-Vilenkin theorem creates a crisis. In 2003, these three physicists proved mathematically that eternal inflation cannot be eternal into the past. Any universe undergoing inflation must have had a beginning. You can trace the inflating region backward in time, but eventually you hit a boundary. A moment before which inflation wasn't happening. This theorem doesn't tell us what happened at that boundary. It doesn't tell us what came before. It just proves that there must be a before, a moment when inflation began, a point where explanation is still required. Some physicists argue the boundary might be a quantum fluctuation from nothing, connecting eternal inflation back to the quantum vacuum theory. Others suggest the boundary might be a previous contracting phase, connecting to cyclic models. Still others propose that the boundary represents a fundamental limit of our theories, a place where general relativity breaks down and quantum gravity takes over. But we don't have a complete theory of quantum gravity. String theory offers one approach. Loop quantum gravity offers another. Each approach suggests different physics at the boundary, different answers to what came before. String theory, for instance, proposes that reality is fundamentally composed of tiny vibrating strings, existing in 10 or 11 dimensions. Most of these dimensions are curled up so small we can't detect them. But in the early universe, near the Big Bang, these extra dimensions might have been large. The boundary of eternal inflation might be a transition point where the geometry of space-time itself changes, where dimensions expand or contract, where the laws of physics transform into something unrecognizable. Loop quantum gravity takes a different approach. It suggests that space itself is quantized, made of discrete units called spin networks. At the Planck scale, the smallest possible scale of length, space becomes grainy, pixelated, fundamentally discrete. In this theory, the Big Bang might not be a singularity at all. It might be a big bounce, a moment when a previous contracting universe reached maximum density and then rebounded, expanding into our current universe. Each theory paints a different picture of cosmic origins. Each theory suggests different physics at the boundary, and we don't yet know which, if any, is correct. This brings us back to the Hartle-Hawking no-boundary proposal. Because this theory takes a radically different approach, instead of asking what came before the Big Bang, it suggests the question itself is meaningless. Stephen Hawking spent years developing this idea with James Hartle. They used a mathematical technique called Euclidean quantum gravity, where time is treated as an imaginary number. This sounds bizarre, but it's a standard technique in quantum mechanics, and it produces real, testable predictions. In this framework, as you trace the universe backward toward the Big Bang, time gradually becomes space-like. The distinction between past and future blurs. The universe doesn't have a beginning in time because time itself emerges gradually from a state where it doesn't exist. Think of it this way. On Earth, you can walk north until you reach the North Pole. But at the North Pole, the concept of north becomes meaningless. Every direction is south. There's no edge, no boundary, no point where Earth suddenly stops. The surface is finite but boundless. Similarly, the universe might be finite in time but boundless. You can trace cosmic history backward for 13.8 billion years, but as you approach the Big Bang, time transforms into space. The universe doesn't have a beginning because the concept of beginning requires time, and time didn't exist in the form we understand it. This is mathematically elegant. It resolves the paradox of cosmic origins without requiring a cause or a creator. The universe simply is, self-contained, requiring no external explanation. But it's also deeply counterintuitive. It violates our basic understanding of causality. It suggests that the universe emerged from a state where time didn't exist, not because something caused it to emerge, but because the mathematics of quantum gravity allowed it to emerge. And here's the problem. We can't test this theory. Not yet. Not with current technology. The no-boundary proposal makes predictions about the quantum state of the early universe, about the pattern of temperature fluctuations in the cosmic microwave background, about the distribution of galaxies across space. Some of these predictions match observations. Others are ambiguous, and some versions of the theory have been ruled out by recent data. In 2017, Hawking and his colleague Thomas Hertog published a revised version of the no-boundary proposal, incorporating new insights from string theory. This version makes different predictions, some of which might be testable with future observations. But Hawking died in 2018, leaving the theory incomplete, still evolving, still debated. The truth is, we're still groping in the dark. We have multiple theories, each mathematically consistent, each explaining some aspects of cosmic origins, but none explaining everything. We have observations that constrain these theories, that rule out some possibilities and support others, but not enough observations to definitively choose between them. And underlying all these theories is a deeper question. Why these laws of physics? Why quantum mechanics? Why general relativity? Why do the fundamental constants have the values they have? Why is the universe comprehensible at all? Some physicists argue these questions are meaningless. The laws of physics simply are. They're the bedrock of reality, requiring no deeper explanation. Asking why the laws exist is like asking why mathematics is true. It's a category error, a confusion of logical levels. Others argue that in an infinite multiverse, all possible laws exist somewhere. We observe these particular laws because we exist in a universe where these laws allow life to form. This is called the anthropic principle, and it's deeply controversial. Some physicists see it as a profound insight. Others see it as giving up on explanation, as declaring that the universe is fundamentally arbitrary. But perhaps the most unsettling possibility is that we're asking questions our brains aren't equipped to answer. Evolution shaped our minds to understand medium-sized objects moving at medium speeds. We're good at tracking prey, avoiding predators, navigating social hierarchies. We're not naturally equipped to understand quantum mechanics or general relativity or the origin of time itself. Every intuition we have about causality, about time, about existence, is based on our experience in this universe, at this scale, with these laws of physics. When we try to think about what came before the universe, we're using concepts that might not apply. We're like fish, trying to understand what it means to be dry, using only concepts derived from living underwater. And yet, we've made progress. We've developed mathematics that describes reality with stunning precision. We've built theories that make predictions confirmed by observation. We've extended our understanding from the everyday world to the quantum realm, to the cosmic scale, to the first fraction of a second after the Big Bang. We've learned that time is relative, that space can bend, that particles can exist in multiple states simultaneously, that the vacuum seethes with quantum activity. We've learned that the universe is stranger than we imagined, and probably stranger than we can imagine. But we keep pushing. We build more powerful telescopes. We construct more sensitive detectors. We develop more sophisticated theories. We test them against reality, refine them, discard the ones that fail, keep the ones that succeed. Because that's what science does. It doesn't claim to have final answers. It offers the best explanations we can construct with current evidence, always provisional, always subject to revision, always open to being overturned by new discoveries. Now let me show you what happens when we actually try to test these theories against reality. Because this is where the beautiful mathematics collides with the messy, complicated universe we actually observe. In 2009, the European Space Agency launched a satellite called Planck. Its mission was simple in concept, revolutionary in execution. Map the cosmic microwave background with unprecedented precision. This faint glow, the afterglow of the Big Bang itself, fills the entire sky. It's the oldest light in the universe, released 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form and light to travel freely through space. The Planck satellite measured temperature variations in this ancient light across the entire sky, down to millionths of a degree. These tiny fluctuations, imprinted in the fabric of space-time during the first fraction of a second after the Big Bang, contain information about cosmic origins. They're like fingerprints left by the birth of the universe itself. And what Planck found was both confirming and deeply puzzling. The data matched the predictions of inflation almost perfectly. The pattern of hot and cold spots, the statistical distribution of temperature variations, the overall geometry of space, everything pointed to a brief period of exponential expansion in the universe's first moments. Score 1 for inflation. But here's where it gets interesting. Different versions of inflation make slightly different predictions. Some predict a universe that's perfectly smooth at large scales. Others predict subtle variations. Some predict gravitational waves from the inflationary period. Others don't. Planck's data ruled out some versions of inflation. The universe isn't quite as smooth as the simplest models predicted. There are anomalies, unexpected features in the data that don't quite match any single theory perfectly. One hemisphere of the sky appears slightly different from the other. There's a mysterious cold spot that's larger than it should be. The universe seems to have a slight preference for certain patterns over others. These anomalies might be statistical flukes, or they might be telling us something profound about cosmic origins. In 2014, a team of astronomers using the BICEP-2 telescope at the South Pole announced they had detected gravitational waves from inflation. The news made headlines worldwide. If confirmed, it would be direct evidence of the inflationary epoch, a smoking gun proving that exponential expansion actually happened. But within months, other teams showed the signal was contaminated by dust in our own galaxy. The gravitational waves hadn't been detected after all. The search continues, with more sensitive instruments, better techniques, more careful analysis. But so far, we haven't found them. This matters because gravitational waves from inflation would tell us about the energy scale of the inflationary epoch. They would constrain which versions of inflation are correct. They would help us understand what the inflaton field actually is, how it behaves, what laws govern it. Without this evidence, we're left with dozens of viable inflation models, each making slightly different predictions, each consistent with current observations, but each suggesting different physics at the moment of cosmic origin. Now let's talk about what we can't see, because that's equally important. When you look at the cosmic microwave background, you're seeing the universe as it was 380,000 years after the Big Bang. Before that moment, the universe was opaque. Light couldn't travel freely. It was trapped in a hot, dense plasma of particles and radiation. We can't see through that barrier with telescopes, no matter how powerful. This means we can't directly observe the Big Bang itself. We can't see the moment of cosmic origin. We can only infer what happened based on the evidence left behind, like detectives reconstructing a crime scene from forensic clues. But there's another way to probe the early universe: gravitational waves. Unlike light, gravitational waves can travel through anything. They're ripples in space-time itself, produced by violent cosmic events. And if inflation happened, it should have produced gravitational waves that are still traveling through the universe today, carrying information about the first fraction of a second after the Big Bang. Several experiments are searching for these primordial gravitational waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from colliding black holes in 2015, confirming that these ripples in spacetime are real. But LIGO isn't sensitive enough to detect the faint primordial waves from inflation. Future experiments might be. The Laser Interferometer Space Antenna, LISA, scheduled to launch in the 2030s, will search for gravitational waves from space, where it can detect lower frequencies than ground-based detectors. If primordial gravitational waves exist, LISA might find them. And if it does, we'll have a window into the first fraction of a second after the Big Bang. We'll be able to test inflation directly. We'll be able to measure the energy scale of cosmic origins. We'll be able to constrain theories, rule out models, narrow down the possibilities. But what if LISA doesn't find primordial gravitational waves? What if they're too weak to detect, or don't exist at all? Then we're back to indirect evidence, to subtle patterns in the cosmic microwave background, to theoretical arguments and mathematical consistency. This is the frustrating reality of cosmology. We're trying to understand events that happened 13.8 billion years ago, at energy scales we can't reproduce in laboratories, using evidence that's been filtered through billions of years of cosmic evolution. We're like archaeologists, trying to reconstruct ancient history from a handful of pottery shards, except the pottery shards are temperature fluctuations in the cosmic microwave background, and the ancient history is the origin of time itself. Now let me show you where the skepticism really bites. In 2013, a physicist named Anna Aegis, along with Paul Steinhardt and Abraham Loeb, published a paper arguing that inflation might be unfalsifiable. They pointed out that inflation has become so flexible, with so many different versions and variations, that it can explain almost any observation. If we find gravitational waves, some version of inflation predicted them. If we don't find gravitational waves, other versions of inflation predicted that. If the universe is smooth, inflation explains it. If the universe has anomalies, inflation explains those too. This flexibility makes inflation powerful, but it also makes it dangerous. A theory that can explain everything explains nothing. If inflation can accommodate any observation, then no observation can disprove it. And if a theory can't be disproven, is it really science? This criticism sparked fierce debate. Defenders of inflation argued that specific models make specific predictions and can be tested. The general framework of inflation might be flexible, but individual versions are falsifiable. We've already ruled out some models based on Planck data. We'll rule out more as observations improve. But the critics pushed back. They argued that every time a version of inflation is ruled out, theorists simply propose a new version with different parameters. The theory evolves to fit the data, rather than making bold predictions that risk being wrong. This is how pseudoscience works, they said. This is how theories become unfalsifiable. The debate continues, and it highlights a deep problem in modern cosmology. We're trying to understand unique events that happened once, long ago, under conditions we can't reproduce. We can't run experiments. We can't rewind the universe and watch the Big Bang happen again. We can only observe the universe we have and try to infer what happened. This is very different from other areas of physics. If you want to test quantum mechanics, you can run experiments in laboratories, repeat them thousands of times, measure the results with precision. If you want to test general relativity, you can observe binary pulsars, measure gravitational waves, watch light bend around massive objects. But cosmic origins? We get one universe, one set of observations, one chance to get it right. And the observations are limited by fundamental barriers. We can't see before the cosmic microwave background. We can't probe energy scales higher than particle accelerators can reach. We can't test theories that make predictions about other universes, or other cycles, or regions of spacetime we can't access. This is where physics becomes uncomfortably close to philosophy. We're forced to make judgments about which theories are more elegant, more natural, more likely to be true, based on criteria that aren't purely empirical. We're forced to trust mathematics, to believe that equations describing reality at scales we can observe will continue to work at scales we can't observe. And maybe that trust is justified. After all, general relativity predicted black holes decades before we observed them. Quantum mechanics predicted antimatter before we detected it. The Higgs boson was predicted in the 1960s and discovered in 2012. Mathematics has been an extraordinarily reliable guide to reality. But cosmic origins push mathematics to its limits. The equations of general relativity break down at the Big Bang singularity, producing infinities that signal the theory's failure. Quantum mechanics doesn't include gravity. String theory requires extra dimensions we can't detect. Loop quantum gravity makes predictions we can't yet test. We're working at the edge of what our theories can handle, and we know it. So let me show you what happens when physicists confront this limitation directly. Because some of the most interesting work in modern cosmology isn't about proposing new theories. It's about understanding the limits of what we can know. In 2003, physicist Max Tegmark published a paper analyzing the ultimate limits of cosmological observation. He calculated that no matter how good our telescopes become, we can never see beyond a certain distance. The universe is expanding, and distant galaxies are receding from us faster than light can travel. There's a cosmic horizon, a boundary beyond which light will never reach us, no matter how long we wait. This horizon is currently about 46 billion light-years away. Everything beyond that distance is forever invisible to us. We can't observe it, can't measure it, can't test theories about it. It's fundamentally inaccessible. Now, here's the disturbing part. If eternal inflation is correct, our observable universe is just a tiny bubble in an infinite, inflating multiverse. Everything beyond our cosmic horizon might be radically different. Different laws of physics, different constants, different dimensions. We can theorize about these other regions, but we can never observe them. They're forever beyond the reach of empirical science. This raises a profound question. If a theory makes predictions about regions we can never observe, is it scientific? Can we claim to know something about reality if we can never test it? Some physicists say yes. They argue that if a theory makes testable predictions about our observable universe, and those predictions are confirmed, then we should trust the theory's predictions about unobservable regions too. If inflation explains what we see, and inflation predicts a multiverse, then the multiverse probably exists, even if we can't observe it directly. Others say no. They argue that science is fundamentally about empirical observation. If you can't test a prediction, it's not science, it's metaphysics. The multiverse might exist, but claiming to know it exists based on untestable extrapolations is overstepping the bounds of scientific knowledge. This debate isn't just academic. It affects how we think about cosmic origins. Because all the major theories, cyclic universes, quantum fluctuations, eternal inflation, the no-boundary proposal, make claims about regions or times we can't observe. They extrapolate from what we can see to what we can't see. They use mathematics to bridge the gap between observation and origin. And maybe that's the best we can do. Maybe the origin of the universe is fundamentally beyond direct observation, and we're forced to rely on indirect evidence, mathematical consistency, and theoretical elegance. But here's what keeps me awake at night. What if our mathematics is wrong? Not wrong in the sense of making incorrect predictions about what we can observe, but wrong in the sense of not applying to cosmic origins at all. Think about it this way. General relativity works brilliantly for describing planets, stars, galaxies, even black holes. But at the Big Bang singularity, it produces infinities. The theory breaks down. It's telling us, in the clearest possible way, that it doesn't apply to that moment. Quantum mechanics works brilliantly for describing atoms, particles, even the quantum vacuum. But it doesn't include gravity. At the Planck scale, where quantum effects and gravitational effects are equally important, we don't know what happens. We have candidate theories, string theory, loop quantum gravity, but we don't know which, if any, is correct. So when we use these theories to extrapolate backward to the Big Bang, we're using tools that we know break down at exactly the moment we're trying to describe. We're like someone trying to measure the temperature of the sun with a thermometer that melts at 1,000 degrees. The tool fails precisely when we need it most. This doesn't mean we should give up. It means we should be humble about our conclusions. It means we should recognize that our theories of cosmic origins are provisional, speculative, built on foundations that might not hold. And yet, we've learned so much. We know the universe is 13.8 billion years old. We know it's expanding. We know it was once hot and dense. We know the cosmic microwave background exists and matches the predictions of the Big Bang theory. We know the abundance of light elements, hydrogen, helium, lithium, matches what we'd expect from nuclear reactions in the early universe. These aren't speculations, these are observations, confirmed by multiple independent methods, accepted by the entire scientific community. The Big Bang happened. The universe had a beginning. That much is certain. What's uncertain is what came before, or whether, quote, 12 even makes sense. What's uncertain is the mechanism that started the Big Bang, the physics that governed the first fraction of a second, the reason the universe exists at all. And this uncertainty isn't a failure of science. It's a reflection of how hard the problem is. We're asking the deepest possible question about reality, and we're doing it with brains that evolved to hunt gazelles on the African savanna. The fact that we've made any progress at all is remarkable. But let me show you one more thing. One more piece of evidence that might, just might, give us a clue about cosmic origins. In 2016, astronomers using the Hubble Space Telescope measured the expansion rate of the universe with unprecedented precision. They looked at distant supernovae, at the cosmic microwave background, at the distribution of galaxies across space. And they found something strange. The universe is expanding faster than it should be. The expansion rate measured from nearby objects doesn't match the expansion rate inferred from the cosmic microwave background. The discrepancy is small, but it's statistically significant. It's been confirmed by multiple independent teams using different methods. This is called the Hubble tension, and nobody knows what's causing it. Maybe it's a measurement error. Maybe it's new physics. Maybe it's telling us something about the early universe, about inflation, about the nature of dark energy. Or maybe it's telling us that our models of cosmic origins are missing something fundamental. Maybe the universe didn't evolve exactly the way we think it did. Maybe there was an additional phase of expansion, or a period of contraction, or some other process we haven't accounted for. The Hubble tension is still being investigated. More observations are being made. More precise measurements are being taken. And every new piece of data either deepens the mystery or points toward a solution. This is how science works at the frontier. You make observations. You find anomalies. You propose explanations. You test them. Sometimes the anomalies disappear with better data. Sometimes they reveal new physics. Sometimes they overturn entire theories. And cosmic origins is the ultimate frontier. We're probing the beginning of time itself, using tools that barely existed a century ago, asking questions that humans have wondered about for millennia. We don't have all the answers. We might never have all the answers. But we're closer than we've ever been. We've gone from mythology to mathematics, from speculation to observation, from philosophy to physics. We've learned that the universe is stranger than we imagined. Time is relative, space can bend, particles can exist in multiple states simultaneously. The vacuum seethes with quantum activity. The universe emerged from a state of extreme density and temperature 13.8 billion years ago. And we've learned that the deepest questions remain open. What came before the Big Bang? Why does the universe exist? Why these laws of physics? Why something rather than nothing? These questions might have answers. Or they might not. The universe might be fundamentally explicable, governed by laws we can discover and understand. Or it might be fundamentally mysterious, containing aspects that are forever beyond human comprehension. But here's what I find most remarkable. We're asking these questions at all. We're not content with mythology or revelation. We're not satisfied with "God did it" or "it's always been this way." We're using observation, mathematics, and reason to probe the deepest mysteries of existence. We're building telescopes that can see nearly to the moment of the Big Bang. We're constructing theories that describe the first fraction of a second after cosmic origins. We're testing these theories against reality, refining them, improving them, getting closer to the truth. And even if we never find the final answer, even if cosmic origins remain forever mysterious, the search itself is worthwhile. Because in searching, we've discovered so much else. We've mapped the universe from the smallest quarks to the largest galaxy clusters. We've understood the life cycles of stars, the formation of galaxies, the evolution of cosmic structure. We've learned that we're made of stardust, that the atoms in our bodies were forged in the hearts of dying stars billions of years ago. We've learned that the universe is vast beyond comprehension, ancient beyond imagination, and yet comprehensible to creatures like us, evolved on a small planet orbiting an ordinary star in an ordinary galaxy. That's the real miracle. Not that the universe exists, but that we can understand it. Not that there was a Big Bang, but that we can figure out it happened, measure when it happened, describe what happened in the moments after it happened. We're the universe becoming conscious of itself, asking questions about its own origins, using mathematics and observation to probe its own history. We're stardust, contemplating the stars, quantum fluctuations, wondering about quantum fluctuations, patterns of matter and energy, trying to understand the patterns that created them. And maybe that's enough. Maybe the search for cosmic origins isn't about finding a final answer. Maybe it's about the search itself, about pushing the boundaries of human knowledge, about refusing to accept mystery as an endpoint, about always asking the next question, always looking deeper, always trying to understand. Because that's what makes us human, not our ability to find answers, but our refusal to stop asking questions. But now I need to tell you something that most physicists are reluctant to admit publicly. Something that makes this entire quest both more profound and more unsettling than you might imagine. We've been talking about theories, observations, mathematical frameworks. We've explored cyclic universes, quantum fluctuations, eternal inflation, the no-boundary proposal. We've examined the evidence, discussed the limits of observation, confronted the boundaries of testability. But there's a deeper problem lurking beneath all of this. A problem that strikes at the very heart of how we do science. The problem is this. We might be using the wrong language entirely. Let me show you what I mean. When we ask, quote 1.5, we're using words like before and came and what. These words carry assumptions. They assume time flows in a particular direction. They assume causality works the way it does in everyday experience. They assume there's a clear distinction between past and future, between cause and effect, between something and nothing. But what if these assumptions break down at cosmic origins? What if the very concepts we're using to ask the question are inadequate to the task? Think about how we describe quantum mechanics. We say particles are in superposition, existing in multiple states simultaneously. We say they collapse into definite states when observed. We say they're, quote, 21, quote, across vast distances. But these are metaphors, borrowed from everyday experience, stretched to describe phenomena that have no everyday equivalent. An electron isn't really in two places at once, the way you might be uncertain whether your keys are in your pocket or on the table. Quantum superposition is something fundamentally different, something our language wasn't designed to capture. We use words like, quote, 22 and, quote, 23. But an electron is neither a wave nor a particle. It's something else entirely. Something we can describe mathematically, but struggle to visualize or articulate in ordinary language. Now scale this problem up to cosmic origins. We're trying to describe a state where time doesn't exist, where space is infinitely compressed, where the laws of physics as we know them break down. And we're trying to do it using concepts derived from our experience in a universe where time flows, space extends, and physical laws are stable. It's like trying to describe color to someone who's been blind from birth. You can use analogies. Red is warm like fire, blue is cool like water. But these analogies don't capture what color actually is. They're translations into a different sensory modality, and something essential is lost in translation. This is what physicists call the problem of interpretation. And it's not just a problem for cosmic origins, It's a problem that runs through all of fundamental physics. In 1927, physicists gathered in Brussels for the fifth Solvay conference. The topic was quantum mechanics, and the debate was fierce. Albert Einstein argued that quantum mechanics must be incomplete, that there must be hidden variables determining particle behavior, that God doesn't play dice with the universe. Niels Bohr argued that quantum mechanics is complete, that randomness is fundamental, that we must accept the theory's strange implications. The debate continued for decades. And here's what's remarkable. Nearly a century later, we still don't have consensus on what quantum mechanics means. We have the mathematics. We can calculate probabilities with stunning precision. We can predict experimental outcomes with extraordinary accuracy. But we don't agree on what's actually happening. Is the wave function real or just a mathematical tool? Do particles have definite properties before measurement, or do properties only exist when observed? Does the universe split into multiple branches every time a quantum measurement occurs, or does the wave function collapse into a single outcome? These aren't idle philosophical questions. They're questions about the nature of reality itself. And after a century of quantum mechanics, we still don't have answers. Now apply this to cosmic origins. We have theories: inflation, cyclic universes, quantum fluctuations. We have mathematics that describes these theories. We have some observational evidence that constrains them. But do we understand what these theories actually mean? Do we understand what it means for the universe to emerge from nothing, or for time to not exist, or for reality to be fundamentally probabilistic? I would argue we don't. Not really. We have mathematical descriptions. We have analogies. We have ways of talking about these concepts that make them seem comprehensible. But the actual reality these theories describe might be so alien to human experience that genuine understanding is impossible. Let me give you a concrete example. The no-boundary proposal uses imaginary time. In the mathematics, time is treated as an imaginary number, a number involving the square root of -1. This is a standard technique in quantum mechanics, and it produces real, testable predictions. But what does it mean for time to be imaginary? Stephen Hawking suggested that imaginary time might be the real time, and what we experience as time is just a special case, an emergent property that appears in certain conditions. In the quantum state of the universe, near the Big Bang, time might be fundamentally imaginary, and the distinction between time and space might not exist. But try to visualize that. Try to imagine what it would be like to experience imaginary time. You can't. The concept is mathematically precise, but experientially meaningless. We can manipulate the equations, derive predictions, test them against observation, but we can't claim to understand what imaginary time actually is. This is the gap between mathematical description and genuine comprehension. And it's a gap that widens as we probe deeper into fundamental physics. Now, I know what you're thinking. You're thinking this sounds like giving up. If we can't understand cosmic origins, if our concepts are inadequate, if the reality is too alien for human comprehension, then why bother? Why not just accept mystery and move on? But here's the thing. Recognizing the limits of understanding isn't the same as giving up. It's being honest about what we know and what we don't know. It's distinguishing between mathematical description and genuine comprehension. It's acknowledging that the universe might be stranger than we can imagine, while still pushing to imagine it as best we can. And there's something profound in this recognition, because it means the universe isn't obligated to make sense to us. Reality doesn't have to conform to human intuition. The cosmos doesn't care whether we can visualize it or articulate it in everyday language. It simply is what it is, and our job is to describe it as accurately as possible, even if that description transcends ordinary understanding. This is what separates science from other ways of knowing. Science doesn't claim to provide comfortable answers. It doesn't promise that reality will be comprehensible or meaningful or designed for human understanding. It offers the best descriptions we can construct with current evidence, always provisional, always subject to revision, always honest about uncertainty. And when it comes to cosmic origins, the honest answer is, we don't know. We have theories, we have evidence, We have mathematical frameworks, but we don't have certainty. We don't have a complete picture. We don't have a final answer. Some physicists find this frustrating. They want closure. They want to solve the problem of cosmic origins and move on to other questions. They want a theory of everything, a final framework that explains all of physics, including the origin of the universe itself. But other physicists find this uncertainty liberating. It means there's still mystery in the universe, still frontiers to explore, still questions that will occupy human minds for generations to come. It means we haven't reached the end of physics. We're still in the middle of the story, still discovering, still learning, still being surprised by reality. Let me show you just how surprising reality can be. Because there's one more aspect of cosmic origins we haven't fully explored, and it's perhaps the strangest of all. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics must be incomplete. They described a thought experiment involving two particles that are quantum mechanically entangled. Measure one particle, and you instantly know something about the other particle, even if they're separated by vast distances. Einstein called this, quote, 24, and argued it proved quantum mechanics was missing something. But experiments have confirmed that quantum entanglement is real. Measure one particle, and the other particle's state is instantly determined, regardless of the distance between them. This doesn't violate relativity. You can't use entanglement to send information faster than light. But it does reveal something profound about the nature of reality. Entangled particles aren't separate objects that happen to be correlated. They're part of a single quantum system, described by a single wave function, even when separated by light years. The universe, at the quantum level, is fundamentally non-local. Distant parts of reality are connected in ways that transcend space and time. Now here's where this becomes relevant to cosmic origins. In the first fraction of a second after the Big Bang, the entire observable universe was smaller than an atom. Every particle, every bit of energy, every region of space that would eventually expand into galaxies and stars and planets. All of it was in direct contact, interacting, becoming quantum mechanically entangled. This means the universe might still be fundamentally entangled. Distant galaxies, separated by billions of light years, might be part of a single quantum system. The cosmic microwave background, the afterglow of the Big Bang, might contain patterns of entanglement that encode information about cosmic origins. Physicists are just beginning to explore this possibility. In 2015, Mark van Ramsdonk proposed that space-time itself might emerge from quantum entanglement. In this view, space isn't fundamental. It's not a stage on which events unfold. It's an emergent property, arising from the pattern of quantum entanglement between particles. If this is correct, then asking what came before the Big Bang is asking the wrong question. Space and time don't exist independently. They emerge from quantum entanglement. And at cosmic origins, when the universe was maximally entangled, the concepts of space and time might not apply at all. This is called the, quote, 25 hypothesis, the idea that space-time emerges from quantum information. And it's one of the most radical proposals in modern physics. It suggests that reality is fundamentally informational, that the universe is, at its deepest level, a quantum computer processing information, and that space and time are just the interface through which we experience this computation. I know this sounds like science fiction, but it's based on rigorous mathematics, developed by leading physicists, and it makes testable predictions. We don't know yet if it's correct, but the fact that serious scientists are exploring this possibility tells you how strange the frontier of physics has become. And here's what keeps me up at night. If space-time emerges from quantum entanglement, then the Big Bang wasn't the beginning of time. It was the moment when quantum entanglement organized itself in a particular way, giving rise to the experience of time. Before that moment, if, quote, 26 even makes sense, there might have been a different kind of reality, governed by different principles, described by different mathematics. We might be asking what came before the Big Bang, when we should be asking, what kind of reality allows Big Bangs to emerge? We might be focused on the wrong level of description entirely. This is the deepest lesson of modern physics. Every answer reveals deeper questions. Every solution opens new mysteries. Every theory that explains one phenomenon raises questions about the framework in which that theory operates. We explained planetary motion with Newton's laws, then asked why those laws hold. We explained those laws with general relativity, then asked why space-time curves. We're trying to explain space-time with quantum gravity, and we'll probably end up asking why quantum gravity works the way it does. At some point, explanation must end. At some point, we must accept something as simply given, as the bedrock of reality that admits no deeper justification. But we don't know where that bedrock is. We don't know if we've reached it, or if there are deeper levels still to discover. And maybe that's okay. Maybe the search for ultimate explanation is like the search for the edge of the universe. The closer you get, the farther it recedes. Maybe reality is turtles all the way down, with each level of explanation resting on a deeper level, infinitely. Or maybe there is a final answer, a theory of everything that explains why the universe exists and why it has the properties it has. Maybe we're close to finding it. Maybe it's just beyond our current reach, waiting to be discovered by the next generation of physicists. But here's what I believe. Whether or not we find that final answer, the search itself is worthwhile. Because in searching, we've learned so much. We've discovered that time is relative, that space can bend, that particles can be entangled across vast distances. We've learned that the universe is 13.8 billion years old, that it emerged from a state of extreme density and temperature, that it's still expanding and evolving. We've learned that we're made of stardust, that the atoms in our bodies were forged in the hearts of dying stars. We've learned that the universe is vast beyond comprehension, containing 2 trillion galaxies, each with hundreds of billions of stars, many of those stars with planets, some of those planets possibly harboring life. We've learned that we're not the center of the universe. We're not special in terms of location or composition. We're ordinary matter on an ordinary planet orbiting an ordinary star in an ordinary galaxy. And yet, we're extraordinary in our ability to understand all of this. We're the universe becoming conscious of itself, asking questions about its own origins, using mathematics and observation to probe its own history. That's the real miracle. Not that the universe exists, but that we can understand it. Not that there was a Big Bang, but that we can figure out it happened, measure when it happened, describe what happened in the moments after it happened. And even if we never answer the question of what came before the Big Bang, even if that question turns out to be meaningless or unanswerable, we've still accomplished something remarkable. We've pushed human knowledge to its limits. We've confronted the deepest mysteries of existence. We've refused to accept easy answers or comfortable myths. We've done what humans do best. We've asked questions. We've built theories. We've tested them against reality. We've been wrong, learned from our mistakes, and tried again. We've collaborated across generations, building on the work of those who came before us, leaving a foundation for those who come after. And in doing so, we've created something beautiful. Not just knowledge, but a way of knowing. Not just answers, but a method for finding answers. Not just understanding, but a commitment to understanding, a refusal to stop asking questions, a determination to push forward even when the path is unclear. This is the legacy of science. This is what we're building when we study cosmic origins. Not just a theory of the Big Bang, but a civilization that values truth over comfort, evidence over authority, reason over revelation. And maybe that's the real answer to the question of what came before the Big Bang. Not a scientific answer, but a human answer. What came before was everything that led to this moment, to creatures like us asking questions like this. What came before was 13.8 billion years of cosmic evolution, producing stars and galaxies and planets and life and consciousness and curiosity. What came before was the universe preparing to understand itself. So let me tell you what terrifies physicists most. It's not that we might never find the answer. It's not even that the answer might be incomprehensible. It's something far more unsettling. It's the possibility that we're asking the wrong question entirely. Throughout human history, we've asked questions that seemed profound at the time, but turned out to be based on false assumptions. Medieval scholars debated how many angels could dance on the head of a pin. The question seemed meaningful within their framework of reality, but the framework itself was wrong. Angels don't exist. The question was meaningless from the start. What if _27 is our generation's version of that question? What if we're debating the details of a framework that will seem quaint and misguided to future physicists? What if the very concept of _28_ is as obsolete as the concept of angels dancing on pins? This is what keeps theoretical physicists awake at 3 in the morning. Not the complexity of the mathematics, not the difficulty of the observations, but the nagging suspicion that we might be fundamentally confused about the nature of reality itself. And yet, here's what's remarkable. Even if we are confused, even if our current theories are wrong, we're confused in increasingly sophisticated ways. We're wrong at deeper and deeper levels. Each generation of physicists discovers that the previous generation's understanding was incomplete, but also that it was approximately correct within certain limits. Newton's laws were wrong, but they work perfectly for everyday objects moving at everyday speeds. Einstein's relativity corrected Newton, but Newton's equations are still good enough to send rockets to Mars. Quantum mechanics revealed that Einstein's deterministic universe was wrong, but Einstein's equations still describe gravity with stunning precision. This is how science progresses. Not by finding final truth, but by constructing better and better approximations. Not by answering questions definitively, but by asking better questions. Not by eliminating mystery, but by transforming vague mystery into precise puzzlement. And cosmic origins represents the ultimate precise puzzlement. We know the Big Bang happened. We know when it happened. We know what the universe was like 1 second after it happened, 1 millisecond after, 1 microsecond after. We can describe the physics of the early universe with equations that make testable predictions. But that final moment, that instant of origin, that boundary between existence and non-existence, that remains shrouded in mystery. Not because we're stupid or lazy or unimaginative, but because we're pushing against the fundamental limits of what can be known. Let me show you just how fundamental these limits are. In 1927, Werner Heisenberg discovered the uncertainty principle. You cannot simultaneously know both the position and momentum of a particle with perfect precision. This isn't a technological limitation. It's not that our instruments aren't good enough. It's that the universe itself doesn't contain that information. A particle doesn't have a definite position and momentum simultaneously. The properties are fundamentally uncertain until measured. Now, scale this up. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy. They contain information, and there's a maximum amount of information that can be stored in a given volume of space. This maximum is called the Bekenstein bound, and it suggests that the universe itself has a finite information capacity. If the universe has finite information capacity, then there's a limit to how much we can know about it. There's a limit to how precisely we can describe its state. There's a limit to how far back we can trace its history before quantum uncertainty erases all information about earlier states. This means that even with perfect instruments, perfect theories, and infinite time, we might never be able to determine what came before the Big Bang. The information might simply not exist. It might have been erased by quantum uncertainty, lost in the singularity, destroyed by the very process of cosmic origin itself. This is what physicists mean when they say the question might be meaningless. Not that it's a stupid question or an unimportant question, but that the universe might not contain the information necessary to answer it. The past might be fundamentally uncertain, not because we don't know it, but because it doesn't exist in any definite form. And if that's true, then what does it mean to ask what came before the Big Bang? It's like asking what the electron was doing before you measured it. The electron wasn't doing anything. It was in a superposition of states, not definitely here or there, not definitely spinning up or down. The definite state only emerged when you measured it. Similarly, the universe might not have had a definite state before the Big Bang. It might have been in a quantum superposition of all possible states, not definitely existing or not existing, not definitely having this history or that history. The definite state, our universe, with its particular laws and constants and history, only emerged when what? This is where the analogy breaks down, because in quantum mechanics, measurement causes the wave function to collapse. An observer interacts with the system, and the superposition resolves into a definite state. But who observed the Big Bang? Who measured the universe and caused it to collapse into this particular state? Some physicists argue that consciousness is required for wave function collapse, which would mean the universe couldn't have a definite state until conscious observers evolved. This leads to bizarre implications, that the universe was in superposition for billions of years until the first conscious being looked at it and retroactively determined its history. Other physicists argue that wave function collapse doesn't require consciousness, that it happens automatically through decoherence, through interaction with the environment. But at the Big Bang, there was no environment. The universe was everything. There was nothing outside it to interact with, nothing to cause decoherence, nothing to collapse the wave function. This is the measurement problem in cosmology, and it's one of the deepest unsolved problems in physics. We have a theory, quantum mechanics, that works brilliantly for describing small systems. But when we try to apply it to the universe as a whole, we run into conceptual paradoxes that we don't know how to resolve. And maybe that's telling us something profound. Maybe it's telling us that quantum mechanics, for all its success, is still incomplete. Maybe there's a deeper theory waiting to be discovered, a theory that includes quantum mechanics as a special case but goes beyond it. A theory that can describe the universe as a whole without running into paradoxes. Or maybe it's telling us that the universe is fundamentally paradoxical. Maybe reality doesn't make sense in the way we expect it to make sense. Maybe the universe contains contradictions, impossibilities, features that violate our intuitions about how things should work. This is what I find most unsettling about cosmic origins. Not that we don't know the answer, but that the answer might be something our brains aren't equipped to understand. We evolved to survive on the African savanna. We're good at tracking prey, avoiding predators, navigating social hierarchies. We're not naturally equipped to understand quantum mechanics, or general relativity, or the origin of time itself. And yet, we've made progress. We've developed mathematics that describes reality with stunning precision. We've built theories that make predictions confirmed by observation. We've extended our understanding from the everyday world to the quantum realm, to the cosmic scale, to the first fraction of a second after the Big Bang. But there might be limits. There might be aspects of reality that are forever beyond human comprehension. Not because we're not smart enough, but because our brains are structured in ways that make certain concepts inaccessible. We might be like dogs trying to understand calculus. The information is there, the patterns are real, but the cognitive architecture required to grasp them simply doesn't exist in a dog's brain. Are we dogs trying to understand cosmic origins? Are we missing some crucial cognitive capacity that would make the answer obvious? Or are we on the verge of a breakthrough, one insight away from understanding everything? I don't know. Nobody knows. And that uncertainty is both terrifying and exhilarating. Because here's what we do know. The universe exists. You exist. Right now, in this moment, you're a pattern of matter and energy, organized in a way that allows you to think, to feel, to wonder about cosmic origins. The atoms in your body were forged in the hearts of dying stars billions of years ago. The energy flowing through your neurons was released in the Big Bang 13.8 billion years ago. You are the universe experiencing itself. You are stardust that has become conscious. quantum fluctuations that have organized themselves into a pattern capable of asking questions about quantum fluctuations. And that's extraordinary. Not because it's rare, we don't know if it's rare. Maybe the universe is teeming with conscious beings asking these same questions. Maybe we're one of trillions of civilizations scattered across the cosmos, all wondering about their origins, all building telescopes and theories and trying to understand. Or maybe we're alone. Maybe consciousness is so improbable, so delicate, so dependent on precise conditions that we're the only instance of it in the observable universe. Maybe we're the only beings capable of asking what came before the Big Bang. Either way, it's extraordinary. Because the universe didn't have to produce consciousness. It didn't have to organize itself in a way that allows matter to think. The laws of physics could have been different. The constants could have had different values. The universe could have been sterile, lifeless, incapable of producing anything as complex as a human brain. But it wasn't. The universe produced stars and planets and chemistry and life and evolution and brains and consciousness and curiosity. It produced beings capable of asking questions about their own origins, capable of building theories and testing them, capable of understanding that they're made of stardust. And maybe that's the answer to the question of cosmic origins. Not a scientific answer, but a philosophical one. The universe exists because it can exist. Consciousness exists because the laws of physics allow it to exist. We're asking questions about the Big Bang because the Big Bang produced a universe capable of producing beings who ask questions. This is called the anthropic principle, and it's deeply controversial. Some physicists see it as a profound insight. Others see it as giving up on explanation, as declaring that the universe is fundamentally arbitrary. But maybe it's neither. Maybe it's just recognizing that some questions don't have the kind of answers we expect. Maybe asking why the universe exists is like asking why mathematics is true. It's a category error, a confusion of logical levels. Mathematics doesn't need a reason to be true. It simply is true. And the universe operates according to mathematical laws because that's what it means for the universe to exist. Similarly, the universe doesn't need a reason to exist. It simply does exist, and we exist within it, and we're capable of asking questions about it. That's not an explanation, but it might be the only answer we're going to get. And you know what? I find that strangely comforting. Because it means the universe isn't obligated to make sense to us. Reality doesn't have to conform to human intuition. The cosmos doesn't care whether we can understand it or not. It simply is what it is, and our job is to describe it as accurately as possible, even if that description transcends ordinary understanding. This is the beauty of science. It doesn't promise comfortable answers. It doesn't guarantee that reality will be comprehensible or meaningful or designed for human understanding. It offers the best descriptions we can construct with current evidence, always provisional, always subject to revision, always honest about uncertainty. And when it comes to cosmic origins, the honest answer is, we don't know. We have theories, we have evidence, we have mathematical frameworks, but we don't have certainty. We don't have a complete picture. We don't have a final answer. Maybe we never will. Maybe the origin of the universe is fundamentally unknowable, hidden behind an event horizon of quantum uncertainty and mathematical singularities. Maybe the question of what came before the Big Bang is meaningless, like asking what's north of the North Pole. Or maybe we're on the verge of a breakthrough. Maybe the next generation of telescopes will detect primordial gravitational waves. Maybe the next generation of particle accelerators will reveal new physics. Maybe the next generation of theoretical physicists will develop a complete theory of quantum gravity that explains cosmic origins with the same precision that general relativity explains planetary orbits. I don't know which future we're heading toward. Nobody does. But I know this. The search is worthwhile. Because in searching, we've learned so much. We've discovered that the universe is stranger than we imagined, and probably stranger than we can imagine. We've learned that time is relative, that space can bend, that particles can be entangled across vast distances. We've learned that we're not the center of the universe, We're not special in terms of location or composition. We're ordinary matter on an ordinary planet orbiting an ordinary star in an ordinary galaxy. And yet, we're extraordinary in our ability to understand all of this. We're the universe becoming conscious of itself. We're stardust that has learned to wonder about stars. We're quantum fluctuations that have organized themselves into patterns capable of asking questions about quantum fluctuations. And maybe that's enough. Maybe the search for cosmic origins isn't about finding a final answer. Maybe it's about the search itself, about pushing the boundaries of human knowledge, about refusing to accept mystery as an endpoint, about always asking the next question, always looking deeper, always trying to understand. Because that's what makes us human. Not our ability to find answers, but our refusal to stop asking questions. Not our certainty, but our curiosity. Not our knowledge, but our wonder. Remember how we began? I asked you to imagine something that may not exist, the moment before time began. I asked you to confront the impossibility of thinking about a moment before moments existed. And now, after exploring cyclic universes and quantum fluctuations and eternal inflation and the no-boundary proposal, after examining the evidence and confronting the limits of observation, after pushing physics to its breaking point, we're back where we started, still wondering, still asking, still unable to fully grasp what it means for the universe to have a beginning. But we're not back where we started, because now we know how deep the mystery goes. Now we understand the sophistication of our confusion. Now we recognize that the question itself might transcend our conceptual frameworks. And that's progress. Not the progress of finding answers, but the progress of asking better questions. Not the progress of eliminating mystery, but the progress of transforming vague mystery into precise puzzlement. The universe exists. You exist. And in this moment, you're thinking about cosmic origins, about the Big Bang, about what came before. Your neurons are firing, processing information, constructing models of reality. You're using a brain that evolved to hunt gazelles to contemplate the origin of time itself. That's absurd. That's beautiful. That's terrifying. That's human. And maybe, just maybe, that's the point. Maybe the universe produced consciousness not to answer questions about cosmic origins, but to ask them. Maybe we're not here to solve the mystery, but to appreciate it. Maybe the search is the destination. So what came before the Big Bang? I don't know. Nobody knows. Maybe nobody will ever know. Maybe the question is meaningless. Maybe the answer is incomprehensible. Maybe we're asking the wrong question entirely. But we're asking. And that's what matters. We're looking up at the stars and wondering where they came from. We're building telescopes and theories and trying to understand. We're refusing to accept easy answers or comfortable myths. We're pushing forward, even when the path is unclear, even when the destination might be unreachable. Because that's what humans do. We ask questions. We seek understanding. We refuse to stop wondering. And in a universe that emerged from nothing, or from quantum fluctuations, or from eternal inflation, or from a state where time didn't exist, in a universe that might be fundamentally inexplicable, that refusal to stop wondering might be the most extraordinary thing of all. The universe doesn't owe us answers, but it gave us the ability to ask questions. And maybe that's enough. Maybe that's everything. What came before the Big Bang? Perhaps the better question is, what kind of universe allows beings to ask that question? What kind of reality produces consciousness capable of contemplating its own origins? And the answer to that question is this one, this universe, this reality, the one you're experiencing right now, in this moment, as you think about cosmic origins and wonder about the nature of existence. You are the universe asking questions about itself. You are the answer to the question of what the universe produces when it evolves for 13.8 billion years. And that's not nothing. That's everything.